Greetings and welcome to CSCI 230 Data Structures. So I like to start my introductory programming classes with one of my favorite quotes. Computer science is no more about computers than astronomy is about telescopes. In fact, astronomy isn't about telescopes at all. Astronomy uses the telescope as a tool to study the stars and the universe. In the same way, computer science is not the study of computers, but the study of how to use computers to solve problems. So the computer is a tool that allows us to do things that we couldn't do before. And you don't have to take my word for it of the value of learning to program. Steve Jobs said it, that everybody in this country should learn how to program a computer because it teaches you how to think. Computer science and learning to program a computer is a different way of thinking than how perhaps you may have been taught before. It's very systematic, very methodical, and it actually helps you distill your thought processes into its essential components. And my personal view is that technology is increasingly transforming so many aspects of our lives. And so my question to you, my charge, is that are you going to sit back and let others decide how that technology will be used, or are you going to join in and become a part of that conversation? And that's really what this class is all about, is building your knowledge so you can join this conversation of how, and decide how technology should be used tomorrow, or even today. So what is computer science? Computer science is the study of automated problem solving using digital information. So other areas of science might be concerned with problem solving in the world. So for example, engineering or robotics. With computer science, we're particularly interested in using digital information. So information that can be stored in a computer and encoded as zeros and ones, which is known as binary. So what does a computer scientist do? Well, computer scientists find ways to use computers to solve problems that have never been solved before. So this is in contrast to other areas of technology. So for example, information technology or IT is looking to adapt existing solutions for a particular client's needs and technology needs. So for example, a computer scientist might invent a new way of computers to communicate together or a new networking protocol. And then an IT specialist is going to make that protocol work in practice for a particular company. Perhaps their internal network, they need some communication. And so in this way, computer science and IT are very related. Anyone with a computer science degree is probably going to be well equipped to work in information technology jobs, but information technology or IT person may not be a good fit for computer science jobs. Another area of computer science is also software development. Many computer scientists get jobs building software for particular clients. And so in some sense, software developers are a little bit related to IT in that they're trying to deliver a working solution for a particular client. But software engineering overlaps a little bit more with computer science in general. So data structures and algorithms are considered essential topics in computer science. In some sense, the entire major can be boiled down to data structures as the fundamental component of computer science. And so the question is why? Why is this so critical to computer science? Well, if computer science is concerned with solving problems that have never been solved before, let's look at data structures and algorithms and what they are first. So a data structure is a way to organize information in memory in a computer program. And an algorithm is a precise series of steps to solve a problem. So if a solution that I come up with as a computer scientist, I'm trying to solve new problems. If a solution takes infinite memory, or 10,000 years, infinite time, then it's not really a solution in practice anyways. So the idea here is that if you're going to solve problems that have never been solved before, there's probably a reason it hasn't been solved before. The easy problems, I mean, sometimes they come along if you have a new domain. So a new series of information is suddenly available to computers, and now computer scientists get to work with it. But but predominantly when you're a computer scientist trying to innovate, you're going to be doing it in the realm of data structures and algorithms. You're going to be finding new ways to do things more efficiently, either in terms of time or space. And time and space tend to have trade-offs. We'll often see that we can save time if we use some more memory, right? We can store things, we can cache them for future use. In contrast, we can take less time, we can take less memory if we allow ourselves more time. In general, algorithms can be challenging because giving and following directions can be hard. Have you ever tried to follow a recipe online or tried to follow directions that someone's given you? Well, here's an example Pinterest recipe, rubber ducky cupcakes. Yep, and here's somebody who nailed it. So giving and following directions can be challenging. Thus, algorithms, which are a precise series of steps, or in essence giving directions, can also be challenging. And so whether it's leading someone through a maze, writing a recipe, or giving directions to an unfamiliar location, giving precise directions in an algorithm can be challenging because unlike humans, a computer cannot fix ambiguous directions. For example, if you're following a recipe to bake a cake and it tells you to put the cake in the oven and then add the flour, well, are you going to swap those directions? Do you know intuitively that you need to put the flour in before you put the cake in the oven? Absolutely, but a computer doesn't. A computer does exactly what we tell it, no more, no less, for better or worse. And so we'll need to study how do we give directions precisely. The way the problem-solving process works, both in this class and in general, is that we start with a task, a programming task, or a problem that we want to solve. In this instance, our example problem is how do I automatically find the minimum in a list of numbers? So the programming language we have is a pre-agreed set of instructions that the computer knows. And so you get to pick the programming language in this class that you'd like to use. The first step, though, is that we write an algorithm. And the algorithm is written in pseudocode. And it's a series of steps for any programming language. And then we translate those pseudocode steps of the algorithm into a particular implementation in a particular programming language. And then we run the program to solve the problem and test out that our solution works correctly. So our next step in this class is to start playing with pseudocode. So again, in this course, you get to pick your target programming language for the projects and all implementation activities, which means the language for the course is going to be pseudocode. So all code that's shared during class, that's assessed on quizzes and exams, is going to be in the form of pseudocode. So what is that? Pseudocode is a blend of English and code, and there's some examples on the screen here. And you get to pick your favorite elements from any programming language. This is my favorite part. So I program in Perl, and Python, and Java, and Bash, C, C++, tons of different languages. And I get to pick my favorite components from all of them and throw them in here. And in fact, you'll see many of my favorite components showing up in the pseudocode. So some students have the question, well, if pseudocode's like a blend of English and code, how close to code does it need to look and how close to English can it look? And so here's my acid test. Pseudocode should be precise enough that when handed to two different programmers, their code results in the same output for most inputs. So if you took one piece of pseudocode, like for example this what function on the left here, if you handed that pseudocode to two different programmers and they coded up and implemented a solution, the output should be the same given the same input. If it's not, then your pseudocode is not precise enough. And part of the goal of the first homework is to give you feedback on what pseudocode looks like. Okay, so we can grow together and learn what pseudocode should look like. Here we have the first homework assignment in this course, which is reading and writing pseudocode. And so the first step is to look at these example pseudocode and see if you can predict what the output would be. You can always check your answers by typing up the pseudocode and converting it into your programming language of choice, but try it on your own first. And then I'm asking you to practice writing pseudocode. So I've given you some sample function problems that I'd like you to try to write. You can code them up yourself if you prefer, but either way, you want to practice writing pseudocode because pseudocode will be the language that we use on exams and quizzes, and it's a really foundational skill to be able to express yourself in a concise form like pseudocode. I look forward to looking at over your solutions. For submitting this assignment, you can either you have a couple different options. You can print out this sheet and write on it and then take a screenshot, just a picture with your phone. You can type your solutions right into the document or share it in whatever form you think works best. For homeworks in general, I assess them based on their completeness, not correctness. And so this gives us an opportunity for me to give you feedback on what your pseudocode looks like, because pseudocode, in some sense, is one of those things where you know it when you see it. And so it's hard to define. I don't want to define it so specifically that you lose your sense of autonomy and expression in the pseudocode. However, I've given you some examples of pseudocode. It's very flexible. If you're concerned, you can always err on the side of it being too close to code. But you don't want it to err on the side of too close to English, because then you risk being imprecise. I look forward to seeing your submission.